Hello, how's it going? My name is Douglas Wilklow. During the spring semester of 2021, am taking control of mobile robots here. So this is Lab 1, distance.py, orientation, rectangle, and circle. So I'll just walk through these one by one. Essentially, the epoch has to be put through all these like trials. First one is distance. I have x set to 10 here, so it should move forward 1 square's length. And y is 5, so the time it's going to be doing that over is 5 seconds. So I'm just going to run it. All right, perfect. And it gives a little message, moved 10 inches in 5 seconds. So essentially how this works is you're going to see formulas like this a lot in my other tasks as well. Essentially what I did was I found the... No, I didn't. I used the actual angular velocity formula off of the slides, and I divided it by 2, which seemed to have fixed whatever problem I was having, where it was just doing double the distance it was supposed to be doing. So I just added that at the end. I had a little comment about that too. But essentially what it does down here in the actual loop where the stuff happens is the only check it makes is if phi is too high. It'll actually just give you an error message and say the speed required to go that far in that little time is too much for the motors. Because anything above 6.28, the motors will just like break, and you actually can't run it. Let me give you an example. Let's say let's go 50. Let's try 50 for funsies. Yeah, the speed required to go 50 inches in 5 seconds is too high for the motors. So onto orientation.py. Essentially what this one's supposed to be doing is, let me just change this over. All right, so what this one does is it'll turn a number of degrees specified by x here. I have it set to 90 because it's a nice pretty number and it looks nice. And y, which is the time it's supposed to be making this turn over the duration of, to be 5 seconds here. Oh yeah, it doesn't crash every time I change the controller. Figure that out. Dude. All right, one more time. All right, perfect. So the way it does that is actually, this one actually calculates the distance, like the size of the circumference of the wheel, you know? And then, oh no, circumference of the wheel is up here. That was actually also in distance up high. But this one actually does something with it, I believe. Yeah, I don't think I used C in there anywhere. Essentially, wheel distance is the amount of distance that I figure the wheel is supposed to be turning over the to turn the puck 90 degrees. So 1/4 of a circle. I figured that the wheels would have to turn 1/4 as well. That turned out to be roughly on the money, but I had to make some adjustments over the time that I was messing around with it. Whole bunch of shenanigans, mathematics went into this, which is probably just some regular formula that I just didn't notice. But that is essentially what goes into phi here. So pi times f times wheel distance, which is the quarter circle of this, like around that much of the wheel that's supposed to be covered. And so f is the rotation per second. So pi times wheel distance should come out to be phi, which is the angular velocity that you want your wheel to be at to make that turn in the specified amount of time. Now down here in the actual loop, what it does is it just literally, it sets, it does the same check that distance does, where if the speed is too high, oh wait, no, it does that down here. If the speed is too high, like it's above 6.28, it'll give you an error message where it says speed required to turn is too high for the motors, and it'll just not do anything. But if everything is okay, everything checks out, what it does is it sets the left motor to velocity of phi and the right motor's velocity to negative phi. So it just has it literally spin in place. Watch that one more time. It's turning 90 degrees over 5 seconds. Beautiful. Wonderful. Look at that. Outstanding. Now, there is a way to do this with the IMU. I am 100% certain, but this used to be triple the length. where I was trying to use the IMU for everything, and it was a big mess. That's where I eventually just decided to go with the kinematics formula for it instead, and just go by how much distance the wheels should be turning in order to make a rotation on this scale. All right, on to rectangle. So very similar to the other two, where it actually takes elements from both of these. This is actually probably my most complicated one. Like, look at this monster. It's a very large while loop that's happening to make the thing move. Where essentially, I actually wound up foregoing the use of X here. Fool that I am. I'm sure that I'm going to lose points for it, but I wound up making it work in a way that was it just timed out so that essentially it breaks the time you're given into eighths. Where is Y? There it is. So 30. Say I made it some multiple of 8, like 24 or something like that. Where each section would be 3 seconds. And each of these 3 seconds, it would go straight, and then it would spend 3 seconds going turning, spend 3 seconds going straight again, spend 3 seconds turning, spend 3 seconds going straight again, turning, and then back to the thing, turn one more time, and then that's 8 motions, 4 straight lines, 4 rotations to make a perfect rectangle, or slightly less than perfect. I think it's off by like an angle or like a degree or so. We'll see. But either way, I'll run this real quick. I believe it's height 10, width 15, so it should probably be like this. Doot. Oh, this is still rotation. All right, so I'm gonna cut that. Probably gonna cut that. So essentially what this is going to do is the height is 10, the width is 15, the time is 30. So over the course of 30 seconds, it's going to go, I believe, up 10 over 15. So it should stop around here, halfway through the second circle, the second square over here. Then come back down, cross, and turn to be right in the same spot it's at right now. So let's just, let's give it 15 seconds to do these things. I bet that's gonna be too fast. Yeah, it's too fast. Okay, so that's actually a good example of the error message. If you don't give it enough time to do the thing, like the motors would just skip or break if you tried to make a move that fast. It just gives you an error message. The speed required for this height is too high for the motors. And then, actually, I should have that break. I'll probably change that after this video. So essentially, what it does, it just boots you out if the kinematics do not work out in its favor. So let's put this here. Let's actually set that to 30. Draw the height first. So that's what it's doing here. Width is false. Turning is false. Now it's turning, so turning is true. Drawing width, so width true, turning false. Now it's going down here again. Now it's going through here again. And now it's going through here again. So it keeps alternating between those over the course of 8 steps. And that's how you build your rectangle. Now on to circle. The last but not least, but actually less complicated than rectangle in my experience. Like way less complicated actually. This one was much more simple. I was very relieved when I got to this and it wasn't destroying my brain. So essentially what this does is I had a kind of wonky way of getting around this where how did I do this exactly? I set it up the same way I did for distance, where I essentially had in my brain distance.pi, where it does a straight line. Imagine that to be the circumference of a circle, just splayed out over this length, you know? And that's what I have as big phi here. So big phi is doing a calculation of exactly what this distance would be if it were just a regular distance translation. So the circumference of the circle that it's supposed to be going around here is what that distance is. So essentially, I'm just going to let it play out here. This is doing a radius of 5 over 20 seconds, by the way. So what it's doing here is the way it works is this whole line here is essentially a line going that way that has been converted through kinematics formulas and all sorts of shenanigans into a circle. But the way it does that is, this is also some kinematics formulas off of the slideshows. It's essentially what makes this move slower than this by a very small amount, but the perfect amount to make it so that when combined, they make that straight line circumference distance formula that is big phi. So I'm pretty sure that's exactly how it's supposed to be done, I hope, because it was simple enough where I was like, oh yeah, that feels about right. I should save that. What did I do? What did I change there? Did I change anything bad? No, okay. So what it does down here is literally just the same thing as the distance robot, where it will just check to see if it's moving too fast. If it is moving too fast, it'll give you an error message. Or if it's trying to move too fast for the allotted time, the amount of distance it's trying to cover over the allotted time, if that's too high, it'll just give you an error message and not move the puck. Otherwise, it will move the guy according to the calculations that are made up here. Perfect. And that is, that's it. That's all of the parts of my project. Thank you.